Long before the cataclysm that marked the end of the Cretaceous period, Earth was an incredibly dynamic and thriving planet, teeming with life that had been evolving for hundreds of millions of years. To truly appreciate how the Great Extinction event unfolded, it's essential to understand the world that existed before it, a world that set the stage for one of the most profound transitions in the history of life on Earth. Imagine a time approximately 100 million years ago, during the mid-Cretaceous period, when the planet was predominantly warmer than it is today. The polar ice caps that now dominate the Arctic and Antarctic regions were either much smaller or completely absent. Sea levels were higher, flooding vast expanses of continents and creating shallow inland seas that dotted the landscape, acting as rich nurseries for marine life. The continents themselves were in the process of drifting apart. Following the breakup of the supercontinent Pangaea in earlier periods, by the late Mesozoic, the landmasses of Laurasia in the north and Gondwana in the south were fragmenting further. This tectonic plate movement caused widespread geological activity, including mountain building, volcanic eruptions, and the formation of new ocean basins and coastlines. These shifting environments contributed to diverse habitats across the globe, supporting a remarkable variety of organisms. In these conditions, life had already advanced tremendously from its modest beginnings in the Precambrian eon. By the time of the Cretaceous, complex ecosystems thrived on land, in the air, and beneath the seas. The dominant terrestrial vertebrates were the dinosaurs, but it would be a mistake to think of this era solely in terms of these magnificent reptiles. The world was alive with other remarkable groups. Early mammals scuttled beneath the feet of giants, primitive birds soared through the skies, and a multitude of insects buzzed among the blooming plants. Flora had also undergone transformative changes throughout Earth's history. Gymnosperms, cone-bearing plants like conifers, had dominated for much of the Mesozoic. But by the Cretaceous period, flowering plants, or angiosperms, were rapidly diversifying. This evolutionary leap played a critical role in reshaping ecosystems, as flowering plants provided new food sources and habitats for insects, herbivorous dinosaurs, and other animals. The relationship between flowering plants and pollinating insects like bees and butterflies was becoming increasingly sophisticated, hinting at the intricate chains of interdependence that are characteristic of modern ecosystems. Marine life flourished under the warm seas. Vast coral reefs built by ancient relative species supported fish of all sizes, from small schooling fish to giant predatory sharks. Ammonites, spiraled, shelled cephalopods, were common, their intricate shells found in fossil beds worldwide, serving as vital index fossils for geologists. Sea reptiles such as mosasaurs and plesiosaurs hunted in these waters, reigning as the marine counterparts to dinosaurs on land. The oceans also hosted early forms of plankton, microscopic organisms that play a fundamental role in the food chain and global biogeochemical cycles. The atmosphere of the time maintained a higher concentration of carbon dioxide than modern levels, contributing to a greenhouse climate. This elevated CO2, coupled with volcanic activity, maintained a temperate and stable environment for life to evolve and flourish. Meanwhile, the sun shone a little more weakly than it does today. But Earth's thick forests and widespread vegetation helped regulate the climate, producing oxygen and providing habitat complexity. In terms of ecosystems, there existed complex habitats ranging from dense tropical forests packed with ferns and early angiosperms to vast open plains where herbivorous dinosaurs grazed in herds. Swamps and wetlands provided breeding grounds for reptiles and early amphibians, and deserts with sand dunes stretched across some continental interiors, shaped by the arid climate regions. The interactions between species were intricate and varied. predators and prey coexisted in a delicate balance. Herbivores evolved defended strategies such as horns, armor, and speed. Carnivores developed various hunting adaptations. Plants, animals, fungi, and microorganisms formed a vast web of life that relied upon the sun's energy, water cycles, and climatic constancy. Jurassic landscapes, rich with towering conifers, cycads, and ferns, had gradually transitioned by the Cretaceous into more varied and modern plant assemblages. This period saw the first emergence of vast forests of flowering plants that would eventually give rise to the ecosystems we recognize today. These forests weren't just scenic backdrops. They were bustling environments where insects pollinated flowers, birds nested in canopies, and small mammals sought shelter. Each species played a nuanced role, weaving a tapestry of biological interactions that sustained Earth's biosphere. While dinosaurs were undoubtedly the most conspicuous creatures, relatively little attention was given to the small mammals of the Mesozoic era at this time, but they were quietly diversifying. Mostly small, nocturnal, and insectivorous, these early mammals were adapted to life under the safety of underbrush and burrows. They would one day inherit the Earth, but for now, they coexisted with dominant reptiles and early birds. This pre-cataclysmic world also experienced natural fluctuations and local extinctions, but the balance of life remained largely intact. Geological records from rock formations, fossil beds, and sediment layers reveal a planet that was fertile and vibrant, with ecosystems functioning in a dynamic but stable manner. Yet, despite this richness and apparent stability, the stage was quietly being set for a series of events that would rapidly shift the trajectory of life on Earth. Subtle clues in the fossil record suggest slight environmental stresses and faunal changes in the final millions of years before the cataclysm. But these were not signs of a globally devastating extinction, rather, indications of evolution continuing as it had over millions of years. In this chapter of Earth's history, life was diverse and expansive. From the thick forests sheltering towering herbivores, to the deep seas teeming with ancient fish and reptiles, and skies filled with the ancestors of modern birds, the mosaic of life was complex and evolving. The climate was warm, carbon dioxide levels were high, and the continents drifted slowly in their endless dance. Volcanoes rumbled and the seas shifted, but the sun warmed the lands and oceans in a familiar rhythm. This was a time when nature thrived, and Earth's living tapestry was rich beyond measure. It was the perfect setting for the rise, dominance, and eventual fall of the dinosaurs. Understanding this context is crucial because it highlights what was lost and why the extinction event was such a cataclysmic rupture. Life as it existed in this golden age was about to change forever, painting the backdrop for the profound and sudden transformation that would conclude the Mesozoic era. Following the rich tapestry of Earth's life before the cataclysm, we now delve deeper into the world that was dominated by one of the most iconic groups of animals, the dinosaurs. Spanning the entire Mesozoic era, which lasted from approximately 252 to 66 million years ago, the age of dinosaurs is marked by extraordinary diversity, dominance, and ecological complexity. This era, also known as the Age of Reptiles, was a time when these ancient creatures were the preeminent terrestrial vertebrates, shaping ecosystems in profound ways. Dinosaurs first appeared during the late Triassic period, around 230 million years ago, but it was during the Jurassic and especially the Cretaceous periods that they reached the peak of their diversity and numbers. Their evolutionary journey was marked by adaptive radiations that allowed them to conquer almost every ecological niche on land. Running through forests, wading in lakes, soaring above, and even burrowing underground, dinosaurs occupied a vast array of habitats with a staggering variety of forms, sizes, and lifestyles. One of the most remarkable traits of dinosaurs was their extraordinary morphological diversity. From the towering, long-necked sauropods, some reaching lengths of over 30 meters, to small, agile theropods barely larger than a chicken, dinosaurs displayed a wide range of body plans and adaptations. Sauropods, such as Argentinosaurus and Brachiosaurus, were colossal herbivores, using their immense size to reach tree foliage and deter predators. In sharp contrast, the theropods, bipedal carnivores, varied from the towering Tyrannosaurus rex to the bird-like feathered velociraptor, combining speed, intelligence, and sharp teeth or claws for hunting. Herbivorous dinosaurs were equally diverse. Besides the titanic sauropods, there were ornithopods like iguanodon and hadrosaurs, commonly called duck-billed dinosaurs, that thrived in herds across broad regions. The ceratopsians, such as Triceratops, sported elaborate horns and frills, likely used for defense, display, or species recognition. Ankylosaurs, the armored dinosaurs, bore thick bony plates and tail clubs, providing formidable protection against predators. Dinosaurs' dominance was not limited to terrestrial environments. The evolutionary cousins of dinosaurs, pterosaurs, ruled the skies. Though technically not dinosaurs, these flying reptiles showcased much variety, from the small bird-like forms to giant species with wingspans over 10 meters. In the ocean, other reptiles such as mosasaurs and plesiosaurs specialized as top marine predators, filling ecological roles similar in some ways to modern whales and sharks. Ecologically, the age of dinosaurs was characterized by complex food webs and interspecies interactions. Large herbivores shaped vegetation patterns through their grazing and browsing habits, influencing the structure of forests and plains. Predators played crucial roles in maintaining ecological balance by culling the weak and stressed populations. Some evidence also suggests social behavior, including pack hunting and parental care, characteristics once thought exclusive to mammals and birds. One of the significant ecological milestones during this era was the rise of flowering plants, or angiosperms, in the mid to late Cretaceous. Their emergence brought profound changes in landscapes and diets. Many herbivorous dinosaurs adapted to browse on these new plants, and the coevolution with pollinators, including insects like bees, altered the ecological networks profoundly. This shift in vegetation may have contributed to diversification in herbivorous dinosaur lineages, expanding food sources and habitat complexity. The ecosystems of the age of dinosaurs were diverse and varied geographically. In what is now North America, vast floodplains supported both massive herds of hadrosaurs and solitary apex predators like Tyrannosaurus rex. Gondwana's southern continents harbored unique groups such as abelisaurids and titanosaurs, displaying different evolutionary paths shaped by their particular environments. Asia, Europe, and Africa each hosted distinct dinosaur faunas, demonstrating biogeographical diversity influenced by continental drift and climate. The behavior and physiology of dinosaurs further illustrate their success and adaptability. Recent fossil discoveries, including evidence of feathers, nesting sites, and growth rates, have reshaped how scientists view these animals. Feathers, once thought to be exclusive to birds, were present in many theropods, possibly for insulation, display, or camouflage. Nesting grounds found in places like Montana and China reveal complex reproductive behaviors, with some species caring for their young. Additionally, dinosaurs were not alone in these ecosystems. Mammals, though small and mostly nocturnal, were diversifying alongside dinosaurs, living under the ecological shadow of these giants. Early birds evolved from small theropod dinosaurs, marking the transition from reptiles to avian species and providing a glimpse into the evolutionary future beyond the extinction event. The age of dinosaurs continued for over 160 million years, reflecting a period of evolutionary experimentation, success, and complexity. Through shifting continents, fluctuating climates, and changing flora, dinosaurs remained dominant, adapting to new challenges and opportunities. Their reign was marked not only by their sheer size or fearsome appearances, but by their remarkable ecological roles and interactions. Understanding the diversity and dominance of dinosaurs also allows us to grasp the magnitude of the extinction that would eventually strike. The ecosystems they built and maintained were intricate and robust, yet vulnerable to sudden, catastrophic disruptions. This juxtaposition of stability and fragility underscores the significance of the final event that would bring the age of dinosaurs to a sudden and dramatic close. As we transition from exploring their age to the specific climatic and geological conditions of the late Cretaceous, we begin to uncover the subtle shifts in Earth's systems that set the scene for profound change. The story of the dinosaurs is not just about colossal creatures, roaming ancient landscapes, but also about the environments in which they thrived and the delicate balances that held life together before the cataclysm disrupted it all. As we transition from the remarkable diversity and dominance of the age of dinosaurs, it becomes clear that the environment in which these creatures thrived was as dynamic and complex as the animals themselves. To fully understand how the Great Extinction event transpired, we must examine the climatic and geological conditions of the late Cretaceous period, the final chapter of the Mesozoic era, spanning roughly from 100 to 66 million years ago. This period was marked by profound shifts in Earth's climate, tectonics, sea levels, and atmospheric chemistry, all woven into a rapidly evolving planet that was gradually edging towards a pivotal transformation. The late Cretaceous was characterized by a generally warm and greenhouse climate, much warmer than today's Earth. Polar ice caps were either very limited or entirely absent, contributing to elevated global sea levels. Estimates suggest seas were about 100 to 200 meters higher than present. This rise in sea levels resulted in vast epicontinental seas flooding across large portions of continents. For example, the Western Interior Seaway stretched deep into the heart of North America, splitting the continent into two land masses and creating extensive shallow marine environments that became hotspots for marine biodiversity. Such high sea levels had a profound impact on land and ocean ecosystems alike. With many continental regions submerged, the available terrestrial habitat was fragmented into islands and peninsulas. This geographic isolation affected species distribution and diversification, fostering evolution in localized pockets, sometimes producing endemic species uniquely adapted to their surroundings. Tectonic activity during the late Cretaceous was vigorous and ongoing. The breakup of the supercontinent Pangaea, which began much earlier, was well advanced and had resulted in the separation of the major continents into configurations that began to resemble today's map, albeit with some major differences. India, for instance, was a drifting island continent moving northward towards Asia, while South America and Africa were moving apart, opening the South Atlantic Ocean. The dynamic movement of tectonic plates contributed both to the formation of mountain ranges — the early stages of the Himalayas began in this period — and to extensive volcanic activity. Volcanism played a critical role in shaping the late Cretaceous environment. The Deccan Traps, in what is now India, represent one of the largest volcanic features on Earth, formed by massive outpourings of basaltic lava during the final few million years of the Cretaceous. These volcanic episodes released enormous amounts of gases, including carbon dioxide and sulfur dioxide, which had significant effects on climate and atmospheric chemistry. Although this volcanism post-dates the onset of some ecological stresses, it was an important factor complicating the global environment, potentially exacerbating climatic fluctuations and acidifying oceans and rainwater. In terms of atmospheric composition, carbon dioxide levels during the late Cretaceous were substantially higher than today's concentrations. Estimates place atmospheric CO2 at roughly 1,000 to 1,500 parts per million, in contrast to modern levels closer to 420 ppm. Elevated CO2 contributed to the warm climate, facilitating lush vegetation growth and augmenting the global carbon cycle. However, it also made ecosystems more vulnerable to rapid changes. Fluctuations could trigger temperature swings and impact ocean chemistry. The oceans themselves were in a state of flux. The oceanic circulation patterns, critical for nutrient distribution and temperature regulation, were influenced by the shifting positions of continents and changing depths of seaways. Warm tropical waters extended far towards the poles, supporting diverse coral reef communities and prolific marine life. Yet, some evidence hints at episodes of hypoxia, areas of low oxygen, in local basins, possibly related to nutrient overloads from increased runoff or disturbances in water circulation. On land, terrestrial climates displayed significant variability depending on latitude and geography. Near the equator, tropical and subtropical climates fostered dense forests with a mixture of conifers, ferns, cycads, and the burgeoning diversity of flowering plants. Moving poleward, the climate gradually cooled but remained temperate, supporting diverse ecosystems that included dinosaurs, early mammals, birds, reptiles, and various plants. The increasing prevalence of flowering plants, which had appeared earlier in the Cretaceous, continued to reshape terrestrial habitats dramatically. Their swift diversification led to changing plant community structures, influencing herbivorous dinosaur diets, insect populations, and petal-driven pollination strategies. This botanical revolution intertwined with climatic conditions to create new ecological niches and adaptive pressures. Paleoclimate proxies, indirect measurements of past climate, such as oxygen isotope ratios in fossilized shells, and sediment analyses, provide evidence for periodic climate fluctuations, including warming pulses interspersed with cooler intervals. These fluctuations, though modest compared to modern climate extremes, hint at environmental instability that might have stressed some biotic communities subtly. Furthermore, sedimentary records reveal episodes of regression and transgression, sea level falls and rises that periodically altered coastal environments and habitats. Such changes could lead to habitat loss, shifts in salinity, and changes in nutrient availability, influencing both marine and terrestrial life. The geological record thus paints a picture of a planet vibrant but occasionally challenged by environmental variability. Importantly, the late Cretaceous lacked permanent polar ice sheets, but growing evidence suggests that some seasonal ice or glacier-like conditions may have existed briefly at high latitudes. This finding suggests Earth's climate was not uniformly warm, and that regional climatic contrasts were emerging, setting the stage for later cooling trends. The tectonic rearrangements also influenced ocean gateways, crucial passages that regulate the flow of ocean currents. For example, the opening and closing of seaways affected the distribution of heat across the planet, influencing regional climates and marine biodiversity. Changes in ocean chemistry, such as fluctuations in carbonate and silica deposition, hint at shifting biological productivity that would ripple through food chains. All these factors, tectonics, volcanism, changing sea levels, atmospheric chemistry, and climate, interacted intricately. Their interplay created a planet where ecosystems had flourished and evolved for millions of years, but were increasingly vulnerable to disruption. The environmental conditions of the late Cretaceous thus provide the essential backdrop for understanding not only the ongoing evolutionary dramas, but also the fragility that preceded the profound extinction at the period's end. By grasping these climatic and geological conditions, we come to see the world on the brink of transformation, a planet where even subtle changes could cascade through ecosystems already finely balanced between stability and flux. This nuanced view sets the stage for the pre-extinction signals recorded in the fossil record, which we explore next. It is here we begin to detect the earliest whispers of a global cataclysm that would forever alter the course of life on Earth. As we venture deeper into the story of how the dinosaurs truly went extinct, our attention turns now to the subtle yet telling clues left behind in the fossil record. Those pre-extinction signals that provide invaluable insights into the biological and environmental transformations unfolding just before the cataclysmic event. Although the final blow came suddenly, the planet had been changing in multiple ways in the lead-up to the extinction, and these signals hidden in sediment layers, fossil assemblages, and geochemical indicators help us reconstruct a world on the verge of upheaval. The fossil record is, in many ways, a magnificent archive of Earth's ancient life, meticulously preserving imprints of species that thrived, adapted, or disappeared. By carefully analyzing the fossil assemblages from the latest Cretaceous strata, scientists have observed patterns of faunal turnover, diversity decline, and ecosystem shifts across various regions and taxa. These patterns, although sometimes complex and debated, reveal that the end Cretaceous extinction was not an entirely instantaneous event, but had precursors and environmental stresses that set the stage. One of the most pronounced observations in the fossil record involves the decline of some dinosaur groups before the impact event. Detailed paleontological studies have shown that certain herbivorous dinosaurs, especially some ceratopsians and hadrosaurs, exhibited shrinking diversity in North America in the final few million years of the Cretaceous. Fossil beds show fewer species and reduced populations, hinting at ecological pressures. However, it is crucial to emphasize that this pattern was not uniform globally. In other regions, such as Asia, dinosaur diversity appeared more stable, indicating a complex, regionally variable scenario. The decline was not restricted to terrestrial organisms. Marine fossils, including ammonites, spiral-shelled cephalopods that were widespread and abundant, also show signs of stress. Ammonite diversity began to wane, leading up to the extinction boundary, and certain lineages displayed morphological abnormalities that could indicate environmental stress, like ocean acidification or temperature fluctuations. Similarly, planktonic foraminifera, microscopic marine organisms used extensively in biostratigraphy, show sudden shifts in diversity and morphology near the same timeline. Another important pre-extinction signal concerns changes in plant communities. Palynological studies, which examine fossilized pollen and spores, reflect a notable downturn in the diversity of flowering plants during the late Maastrichtian stage of the Cretaceous. Some specialized plant taxa decreased sharply, suggesting alterations in climate or habitat availability. These botanical changes would have undoubtedly rippled through the food webs, impacting herbivorous dinosaurs and insects. Geochemical signatures reinforce the narrative of environmental instability. Variations in carbon isotope ratios, D13C, in sedimentary layers indicate perturbations in the global carbon cycle just before the KPG boundary, formerly known as the KT boundary. These anomalies suggest disturbances in organic carbon burial, ocean productivity, or atmospheric composition. Signs of ecological stress akin to the signals observed in modern ecosystems under climatic strain. Volcanic activity, particularly associated with the Deccan Traps in India, is another factor linked to pre-extinction signals. Radiometric dating has shown that some of these massive volcanic episodes coincided roughly with the last few 100,000 years before the extinction event. The release of sulfur dioxide and carbon dioxide from these eruptions could have induced short-term cooling due to aerosols and long-term greenhouse warming, leading to fluctuating climates. Evidence from sediment cores implies repeated ocean acidification events, possibly linked to this volcanism, which likely stressed marine organisms. Additionally, the fossil record reveals evidence of fluctuating sea levels during the late Cretaceous. Transgressive and regressive cycles, in which seawaters rose and fell, altered coastal habitats and disrupted shallow marine ecosystems. These recurrent habitat changes would have challenged stable ecological communities, possibly fragmenting populations and decreasing resilience to further stresses. Looking at vertebrate fossils, some taxa showed patterns of morphological change or dwarfism, which has been interpreted by some researchers as an adaptation to environmental pressures, including limited food resources or habitat shrinkage. However, other studies argue these changes could be attributed to normal evolutionary dynamics. This ongoing debate highlights the complexity of interpreting pre-extinction signals and cautions against oversimplifying the narrative. Despite these signs, it is important to recognize that a majority of dinosaur groups remained diverse and widespread until very close to the extinction boundary. This reinforces the notion that while ecosystems experienced strains and fluctuations, it was not a slow, uniform decline, but rather a system vulnerable to abrupt upheaval. Fossil sites around the world have been crucial in providing high-resolution snapshots of life in those final stages. For example, the Hell Creek Formation in North America offers an exceptionally detailed record of the last terrestrial ecosystems, showing coexistence of various dinosaur species right up to the boundary layer. Similarly, marine strata in regions such as the Gulf coastal plain reveal changes in plankton populations and sediment chemistry coincident with these events. Taken together, these lines of evidence present a picture of a planet under subtle environmental stresses and biological shifts intensified toward the end of the Cretaceous. But they also underscore that the ultimate driver of the mass extinction likely involved a rapid, catastrophic insult, an event that we will explore in the upcoming sections. The fossil record, therefore, serves as a crucial bridge between a flourishing dinosaur-dominated world and the subsequent collapse that reshaped the biological future of Earth. By studying these pre-extinction signals, scientists continue to unravel the complex interplay of gradual environmental change and sudden catastrophe, deepening our understanding of one of the most famous extinction events in Earth's history. In the chronicles of Earth's history, few scientific discoveries have reshaped our understanding of mass extinction as profoundly as the work culminating in what is now known as the Alvarez Hypothesis. This groundbreaking theory, proposed in the early 1980s, marked a seismic shift in paleontology by linking a sudden extraterrestrial impact event to the mass extinction that wiped out the non-avian dinosaurs and countless other species at the close of the Cretaceous period. The backdrop of this discovery begins with physicist Luis Alvarez, his son Walter Alvarez, a geologist, and their interdisciplinary team. While studying rock formations in Gubbio, Italy, Walter Alvarez was investigating sedimentary layers corresponding to the boundary between the Cretaceous and Paleogene periods, then commonly referred to as the KT boundary, now updated to the KPG boundary. This boundary was known as a global stratigraphic marker, a thin layer separating rocks from before and after the extinction event roughly 66 million years ago. What made the Gubbio site remarkable was its pristine sedimentary record, a sliver of clay representing a time interval only a few centimeters thick. yet spanning a world-altering moment. Upon chemical analysis of the boundary clay, the team made a startling discovery: an anomalously high concentration of iridium, a rare transition metal scarcely abundant in Earth's crust, but found in much higher quantities in extraterrestrial objects like asteroids and comets. Iridium's scarcity on Earth, yet abundance in certain meteorites, provided a tantalizing clue. Could this layer of iridium-rich clay be a signature of some extraterrestrial event? The hypothesis the Alvarezes developed proposed exactly that. They suggested that a massive asteroid or comet impact had deposited a global layer of iridium-bearing dust in the Earth's atmosphere, settling worldwide and embedded in this geological boundary. Before this discovery, the dominant theories about the end Cretaceous mass extinction often centered around gradual processes, volcanic activity, sea level changes, and climate variability. The Alvarez hypothesis introduced a bold alternative: that a catastrophic, sudden impact had triggered environmental chaos, causing species extinctions in a geologically instantaneous blink. To test their hypothesis, the research team combed through KPG boundary sites around the world, sampling soils and sediments. Remarkably, they found that this iridium anomaly was not unique to Italy, but present in numerous geographically disparate locations, from Denmark to New Zealand, and even across North and South America. This global presence reinforced the idea of a planet-wide fallout consistent with an impact event. The concentrations of iridium in the boundary layer were often around 30 times higher than normal background levels found in Earth's crust, an extraordinary spike. Additional layers of evidence accumulated: shocked quartz grains, which are microscopic crystals exhibiting patterns of deformation characteristic of high-velocity impacts; microtectites, small glassy spherules formed when molten rock is ejected during hypervelocity collisions; and soot layers indicative of widespread wildfires. Together, these physical signatures formed a compelling case for the asteroid impact theory. The hypothesis elegantly explained the abrupt extinction patterns seen in the fossil record, the global iridium anomaly, and the widespread environmental disruptions inferred from geochemical data. Initially, the idea encountered skepticism. Some scientists found it hard to reconcile such a sudden event with the complex patterns of extinction and survival observed globally. Others argued for terrestrial explanations like intense volcanic activity, which was certainly known to have shaped late Cretaceous Earth through the massive Deccan Traps eruptions in India. Yet over time, as more evidence converged, particularly when the Chicxulub crater was discovered and dated to the very same time frame, the asteroid impact hypothesis gained overwhelming acceptance. The Alvarez hypothesis changed the paradigm of extinction science, highlighting the interplay between Earth and cosmic forces. It underscored that mass extinctions could be driven not only by slow biological and geological changes, but by abrupt extraterrestrial events capable of reshaping life on a planetary scale within a matter of moments. Crucially, this discovery opened new avenues for research, fostering a multidisciplinary approach that combined geology, geochemistry, paleontology, and astronomy. It challenged researchers to look beyond Earth's surface and consider the larger cosmic environment influencing our planet's history. In summary, the discovery of the iridium layer at the KPG boundary ignited a revolution in understanding the dinosaur extinction event. What began as a simple chemical anomaly in a modest clay layer unfolded into a narrative about an impactor from space driving one of the most dramatic biological turnovers in Earth's history, forever altering the trajectory of life. As we proceed, we will explore the physical evidence of this impact more closely, uncovering the crater it left behind and the devastating global consequences that followed. Building upon the groundbreaking Alvarez hypothesis and the discovery of the global iridium anomaly, scientists around the world embarked on a hunt to locate the physical scar left behind by the immense cosmic impact that had reshaped life on Earth some 66 million years ago. What they sought was the impact crater, the telltale geological evidence capable of confirming the asteroid collision theory and revealing details about the cataclysm itself. This quest would culminate in the unveiling of one of the most significant geological features ever discovered: the Chicxulub crater. The search for the crater was challenging. Unlike many impact craters visible on Earth's surface, the Chicxulub crater was buried beneath dense layers of rock, sediment, and ocean waters, concealed from direct observation for millions of years. Its discovery required integrating advances in earth sciences, including marine geology, geophysics, and petroleum exploration. The story of Chicxulub begins in the late 1970s and early 1980s in the Yucatan Peninsula in Mexico. Oil companies operating in this region deployed seismic reflection techniques to map subsurface rock formations in search of potential hydrocarbon reservoirs. These seismic surveys revealed a roughly circular anomaly about 150 kilometers in diameter, an immense circular depression characterized by deformed and displaced rock layers. However, at the time, the feature's significance was not connected widely to the dinosaur extinction. Simultaneously, geologists and impact specialists noted that the size and morphology of the Yucatan structure were consistent with a massive impact crater. This hypothesis gained traction when subsequent drilling programs extracted core samples from inside the structure. These cores contained shocked quartz and other impact-related minerals, confirming the feature's impact origin. Crucially, when geochronological dating techniques were applied, the age of the impact event was determined to be approximately 66 million years, precisely coinciding with the KPG boundary and the timing of the mass extinction. This coincidence provided the strongest evidence yet that the Chicxulub impactor was the cause of the global extinction event. The Chicxulub crater's unique characteristics added further insight into the scale of the devastation. Its diameter, roughly 150 to 180 kilometers, indicated that the impacting body was enormous, estimated to be around 10 to 15 kilometers wide, striking Earth at hypersonic speeds. The collision unleashed 1 trillion tons of energy, equivalent to billions of atomic bombs, reshaping the planet in moments. Structurally, the crater exhibits complex features typical of large impact craters, including a central peak ring formed by the rebound of Earth's crust immediately after the impact, and a multi-ringed basin. Studies of the structure reveal displaced rock layers, melted rock, or impact melt, and breccias, rock composed of broken fragments fused together by the tremendous energy of the impact. Beyond the crater itself, the impact ejected vast quantities of debris into the atmosphere, which then settled globally, creating the iridium-rich layer first observed by the Alvarezes. The ejecta blanket, consisting of tiny molten droplets, glass spherules, and dust, blanketed Earth, reducing sunlight and causing severe climatic disruptions. Another striking revelation came from studying the regional effects around Chicxulub. A massive tsunami triggered by the impact sent towering waves across the Gulf of Mexico and adjoining coastlines, scouring sediments and dramatically altering coastal landscapes. The blast wave destroyed life over hundreds of kilometers, while wildfires ignited across continents due to the intense heat released. Investigations using computer models have helped reconstruct the event with remarkable precision. Simulations show the impact vaporized entire ecosystems virtually instantly. The energy release destabilized the atmosphere, oceans, and biosphere, sending shockwaves through global systems. This multidisciplinary approach, combining geology, geophysics, paleontology, and modeling, has allowed researchers to piece together the catastrophic sequence in stunning detail. Despite the compelling evidence, debates persisted about the crater's significance and the exact mechanisms by which the impact caused extinction. Was it a single lethal blow, or did other factors, like volcanism or climate stress, interplay? Nevertheless, the identification and study of the Chicxulub crater revolutionized Earth sciences and firmly anchored the impact hypothesis in physical reality. The Chicxulub crater, hidden beneath the Yucatan's surface for millions of years, stands as a testament to the colossal forces that shaped Earth's past. It transformed scientific understanding of mass extinctions from gradualistic theories to recognizing sudden extraterrestrial catastrophes. This discovery set the stage for examining the immediate aftermath of the impact, how the planet's systems were jolted and life faced its harshest trials. As we journey forward, the unfolding story of the global cataclysm and its devastating environmental effects will become clearer, grounding abstract theories in the tangible evidence born of that ancient collision. As we step into the profound narrative of the global cataclysm that marked the end of the age of dinosaurs, it is essential to reconstruct the immediate and catastrophic aftermath that unfolded the moment the asteroid collided with Earth. The Chicxulub impact was not merely a singular collision. It was an event of unimaginable power that instantly transformed Earth's environment on a global scale, triggering a cascade of destructive forces that reverberated across land, sea, and atmosphere. Imagine an extraterrestrial object roughly 10 to 15 kilometers in diameter, hurtling toward Earth at velocities exceeding 20 kilometers per second. The moment this giant celestial visitor struck the shallow tropical seas off the present-day Yucatan Peninsula, it unleashed kinetic energy equivalent to billions of atomic bombs detonated simultaneously. This was an instantaneous release of energy so vast it defies everyday human comprehension. Upon impact, the asteroid created a crater over 180 kilometers wide, vaporizing the asteroid itself and a vast volume of rock and sediment. The collision generated extreme heat, pressure, and shock waves that radiated outwards, shattering everything within a radius of hundreds of kilometers. In seconds, the initial blast obliterated forests, flattened landscapes, and incinerated living organisms in the immediate vicinity. Shockwaves generated by the impact propagated through the Earth's crust, triggering intense seismic activity. Earthquakes likely reached magnitudes of 11 or greater, far surpassing any modern tremors. These tectonic jolts extended globally, causing ruptures, landslides, and catastrophic ground shaking thousands of kilometers away. Simultaneously, the intense heat generated by the impact caused rock and sediment to melt and be ejected as molten droplets and dust high into the atmosphere. This ejecta curtain spread around the Earth, forming a layer of fine, iridium-rich dust detected worldwide in the geological record. The rapid settling of this particulated matter darkened the skies, drastically reducing sunlight and hindering photosynthesis. In the minutes following the collision, the heat from re-entering ejecta heated the lower atmosphere to extraordinary temperatures. Infrared radiation from these incandescent particles likely ignited wildfires across vast regions, with flames engulfing forests from North America to Asia. Geological layers rich in soot and charcoal provide evidence of this global wildfire crisis, one of the most devastating consequences of the impact. Simultaneously, the impact displaced an enormous volume of seawater, launching colossal megatsunamis. Waves hundreds of meters high raced across oceans, inundating coastlines worldwide and devastating marine and terrestrial habitats along their path. Coastal sediment deposits bearing scour marks and chaotic sedimentation patterns speak to the violent flooding and erosion caused by these tsunamis. The escalation of damage extended beyond physical destruction. The impact vaporized sulfate-bearing rocks, releasing immense volumes of sulfur dioxide into the atmosphere. This triggered acid rain episodes that acidified soils, freshwater bodies, and oceans, further stressing surviving ecosystems. Acidification events also led to the collapse of sensitive marine organisms, particularly those reliant on calcareous shells. The combination of darkness from dust clouds, cooling from aerosol reflections, and acid rain created a hostile environment known as an impact winter or nuclear winter analog. Temperatures plummeted globally, disrupting climate patterns, rainfall, and growing seasons. With sunlight obstructed, photosynthetic organisms such as plants and phytoplankton suffered massive die-offs, dismantling the foundation of food chains both on land and in the oceans. Nitrogen oxides formed in the atmosphere by the intense heat and shock were also contributors to ozone depletion, allowing increased ultraviolet radiation to strike the Earth's surface after the dust cleared, posing additional challenges to recovering life. This multifaceted assault unfolded within hours to days and persisted for months and years, radically transforming habitats and decimating biodiversity. The immediate effects obliterated countless species outright, while rendering ecosystems unstable and vulnerable to secondary stresses. The fossil record from this transitional moment tells a story of catastrophic loss interlaced with ecological disruption. Many organisms perished instantly or shortly after, while others faced starvation, habitat loss, and disease. The complex interplay of wildfire, tsunami, acid rain, darkness, and cold forged a planetary crisis that few species could survive. Understanding these immediate consequences of the Chicxulub impact deepens our appreciation of the scale and speed of the extinction process. It was not just a single dramatic explosion, but a sequence of interconnected phenomena cascading across global systems, leaving the Earth forever changed. As we continue to unravel the series of events following the impact, we will explore specific phenomena such as wildfire devastation, oceanic transformations, and long-term climatic consequences that together shaped the final fate of the dinosaurs and other forms of life at the close of the Cretaceous. Emerging from the immediate shock of the Chicxulub impact, one of the most haunting and far-reaching consequences was the terrifying global firestorm that engulfed vast regions of the planet. This phenomenon, an inferno sparked by intense heat and atmospheric disturbances, played a pivotal role in shaping the environmental apocalypse that wiped out the dinosaurs and devastated countless other species at the close of the Cretaceous. The firestorm began within moments after the asteroid's impact, fueled by the incredible release of thermal radiation. As the impact vaporized rocks and ejected molten debris high into the atmosphere, countless glowing droplets of molten glass and incandescent rock rained down across the globe. These re-entering ejecta heated the lower atmosphere to temperatures so high that they ignited vegetation, forests, and peatlands thousands of kilometers from the impact site. Geological evidence speaks volumes about these widespread wildfires. Layers of soot and charcoal found in sedimentary strata at the KPG boundary showcase one of the most extensive wildfire events in Earth's history. This global layer indicates that forests across continents, from the lush floodplains of North America to the diverse woodlands of Asia, were simultaneously set ablaze. The scale and intensity of these fires were unlike anything observed in the modern world, enveloping ecosystems in firestorms that consumed organic material and reshaped landscapes. Importantly, these fires weren't isolated incidents, but part of a vast, interconnected environmental cascade. The thermal pulse from the re-entering ejecta created incendiary conditions, triggering simultaneous ignition at multiple locations, compounding the devastation. The massive release of particulate matter and soot further darkened the presiding skies, enhancing the severity of the environmental crisis. Wildfires are well known today for their role in ecosystem cycles, but the KPG firestorm was catastrophic on a planetary scale. The fires not only destroyed habitats, but also released vast quantities of carbon dioxide and other greenhouse gases into the atmosphere, intensifying climatic disruptions. The rapid combustion of biomass released aerosols that contributed to atmospheric opacity, further blocking sunlight in what would become a prolonged period of darkness and cooling known as the impact winter. Beyond the sheer destruction of terrestrial flora and fauna, these fires had cascading effects on the atmosphere's chemistry. The enormous plume of smoke injected soot and other aerosols into the stratosphere, where they could linger for years, reducing solar radiation reaching Earth's surface. This blockage of sunlight profoundly curtailed photosynthesis, starving primary producers such as plants and phytoplankton, the very foundation of most food webs. Additionally, wildfire emissions included nitrogen oxides and other reactive gases, which played a role in degrading the ozone layer. This degradation likely increased the influx of harmful ultraviolet radiation once atmospheric dust began to settle, further stressing surviving organisms, especially those vulnerable to UV damage like amphibians, young plants, and marine plankton. The toxic cocktails produced by burning forests, combining carbon monoxide, volatile organic compounds, and particulate matter, also contributed to atmospheric changes that would have had immediate and lasting respiratory impacts on animals. Survivors of the initial blasts faced inhospitable air quality and environmental toxicity, adding yet another layer to the challenges of survival. Fires and heat waves during this period are considered to have had a selective effect on species. Organisms with the ability to burrow, fly, or find refuges in aquatic environments had better chances of weathering this fiery onslaught. Conversely, large, slow-moving terrestrial animals dependent on dense vegetation became especially vulnerable. Ecological recovery after such a blanket of destruction was slow. It took centuries for forests to reclaim burned landscapes, and the collapse of plant populations had ripple effects up through herbivores to carnivores and omnivores alike. Fossil evidence from post-KPG sediments indicates that in the immediate aftermath, ecosystems were dominated by opportunistic, rapidly reproducing species, often small-bodied and adaptable, capable of surviving in harsh, disrupted environs. Modern impact modeling, laboratory experiments, and geological investigations continue to refine our understanding of these firestorms. They reveal a scenario where the Chicxulub impact didn't only strike Earth physically, but triggered atmospheric and ecological upheaval through fire, soot, and heat, contributing decisively to the mass extinction. This fiery chapter in Earth's prehistory underscores the vulnerability of life to rapid environmental change and highlights the interconnectedness of geological, atmospheric, and biological systems. As the wildfires raged globally, they marked the beginning of a dark period, setting the stage for subsequent phenomena such as megatsunamis, nuclear winter, and acid rain that together sealed the fate of the dinosaurs. In the unfolding tale of extinction, the firestorm stands out as both a symbol and mechanism of the drastic transformation that followed a single devastating cosmic encounter. Understanding it not only illuminates past catastrophes, but offers vital perspectives on how sudden, widespread environmental disasters can cascade through the web of life. The catastrophic asteroid impact at Chicxulub not only generated intense heat and widespread fires, but also unleashed a series of colossal oceanic disturbances whose scale and consequences were as terrifying as the initial blast itself. Among these were the megatsunamis and global flooding events, enormous waves and water movements that reshaped coastlines and marine habitats across the planet, leaving permanent evidence in the geologic record. Unlike ordinary tsunamis caused by earthquakes or smaller volcanic eruptions, the waves triggered by the Chicxulub impact were unprecedented in their magnitude and reach. The collision occurred in a shallow sea region near what is now the Gulf of Mexico, generating an instantaneous displacement of an extraordinary volume of water. This displacement produced waves hundreds of meters high, far greater than any modern recorded tsunami. These giant waves radiated outward at high speeds, smashing into the surrounding continental margins with devastating force. Coastlines around the Gulf of Mexico bore the brunt of the initial onslaught, but the energy propagated across entire ocean basins, sending towering waves racing toward distant shores as well. Geological studies have identified sedimentary deposits consistent with tsunami activity in places as far removed as the western interior of North America, the Caribbean, and even parts of Europe and South America. The physical imprints of these megatsunamis are found in chaotic sediment layers characterized by a mixture of marine and terrestrial materials, including marine fossils thrust atop land sediments and debris layers filled with broken shells, rocks, and organic matter. These deposits, often made of coarse-grained materials laid down rapidly, reveal the sheer intensity and speed of the inundations. In some regions, evidence of backwash patterns and scoured river valleys indicates the forceful retreat of the massive waves, which further eroded landscapes and transported sediments far inland. The presence of large boulders and uprooted trees embedded in tsunami deposits also attests to the destructive capacity of these water flows. These megatsunamis profoundly altered coastal ecosystems. Shores were obliterated, mangroves and forests stripped away, and marine habitats' shallow waters were disrupted by the physical scouring. The destruction extended beyond aquatic life to impact terrestrial animals whose habitats lay near coastlines, wiping out entire communities. Besides the initial waves, the impact likely triggered global-scale flooding events related to the displacement of water and subsequent environmental changes. The sudden shift in sea level caused by the impact, combined with melting of any polar ice, though limited, may have contributed to transient flooding episodes. Meanwhile, disrupted weather patterns and atmospheric conditions induced heavy precipitation and storms that exacerbated flooding inland. These waters carried not only physical destruction, but also chemical changes. Debris and chemicals swept into oceans altered salinity and sediment composition, while the influx of nutrients and aerosols affected marine productivity in complex ways. Acidification events, driven partly by volcanic emissions coinciding with the impact, compounded stress on marine organisms attempting to recover. Fossil assemblages in tsunami and flood deposits reflect sudden mortality events, with a rarity of species diversity and the dominance of fast colonizing organisms. The rapid burial under sediments paradoxically helped preserve these snapshots of ecological collapse and early recovery phases. In addition to shaping ancient sediments, studying megatsunami evidence from the Chicxulub event has increased modern understanding of tsunami generation, propagation, and hazards. It underscores the potential devastation such impacts can unleash and helps scientists develop models to predict consequences of future extraterrestrial collisions. The megatsunamis, combined with concurrent firestorms and atmospheric disturbances, constructed a hostile suite of environmental changes that devastated life on multiple fronts, physically erasing habitats and chemically altering conditions crucial for survival. These overwhelming forces contributed significantly to the mass extinction event, setting life on a trajectory from which recovery would take millions of years. In the larger narrative of the asteroid impact's devastation, the megatsunamis and flooding events represent the watery chaos, an element often overshadowed by fiery destruction, but no less critical in shaping the final fate of many species. As we proceed, we will examine the consequent atmospheric changes, including the profound reduction of sunlight and subsequent nuclear winter phase that further prolonged the planetary crisis. Following the monumental forces unleashed by the asteroid's impact, intense heat, global firestorms, and massive tsunamis, Earth faced yet another profound and long-lasting consequence: a nuclear winter. This term, originally coined to describe the grim aftermath of hypothetical global nuclear war, perfectly captures the scenario that unfolded after the Chicxulub collision, where thick clouds of dust, soot, and aerosols enveloped the planet, blocking sunlight and plunging Earth into darkness and freezing temperatures. The nuclear winter represented an environmental bottleneck of enormous scale, triggering a near collapse of ecosystems and profoundly affecting the survival of countless species. To comprehend this dark period, it is necessary to understand the nature of the atmospheric veil that shrouded the Earth after the impact. The collision vaporized vast volumes of rock and ejected a tremendous amount of particulate matter. Fine dust, pulverized minerals, and microscopic glass spherules into the stratosphere. Simultaneously, worldwide wildfires injected prodigious quantities of soot and carbonaceous particles. Unlike typical dust or smoke that settles relatively quickly, particles reaching the upper atmosphere can linger for months to years, reflecting and absorbing sunlight, thereby severely reducing the amount of solar radiation reaching Earth's surface. Scientific models simulating these effects estimate that sunlight could have been reduced by as much as 90% in the immediate aftermath. This darkness led to a dramatic drop in surface temperatures globally, akin to a deep, widespread winter. Some estimates suggest temperature declines of 10 to 20 degrees Celsius, 18 to 36 degrees Fahrenheit, or more, with harsher cooling near the poles but severe impacts everywhere. This sudden cooling had devastating consequences for photosynthetic life. Plants, algae, and phytoplankton depend on sunlight for photosynthesis, the process by which they convert solar energy into chemical energy and oxygen. With near-total darkness, these primary producers either slowed their metabolism drastically or died off in large numbers. On land, forests withered. In the oceans, phytoplankton blooms collapsed. Since these organisms form the foundational base of food webs, their loss cascaded rapidly through higher trophic levels. Herbivores starved, followed by the predators that fed on them. The disappearance of sunlight also affected global climate systems by disrupting evaporation and precipitation patterns. Reduced heat input slowed atmospheric circulation and altered wind and storm dynamics, creating unpredictable and extreme weather. Many regions experienced droughts, while others saw increased flood events after the eventual clearing of particles. In addition to the direct shading effect, the atmosphere underwent significant chemical changes during the nuclear winter. The injection of sulfur dioxide and other volcanic gases from impact-triggered or concurrent volcanic activity created sulfate aerosols, which further enhanced the reflective capacity of atmospheric particles. These aerosols also contributed to acid rain as they combined with water in the atmosphere, depositing acidic precipitation onto land and oceans. The prolonged absence of sunlight and altered climate conditions placed prodigious physiological stress on animals. Cold-blooded reptiles like dinosaurs, which relied heavily on environmental heat to regulate their body temperature, suffered profoundly. Moreover, the scarce availability of food sources in the aftermath compounded survival challenges. For smaller organisms and those inhabiting stable refuges such as caves, deep ocean environments, or subterranean burrows, the nuclear winter's immediate impact was mitigated somewhat. Many early mammals, and some avian dinosaurs, which could regulate their own body temperature, had better chances of endurance and eventual recovery. Geological evidence hints at the duration of this darkness-related climate crisis lasting years to possibly decades. This time frame aligns with the slow recovery of ecosystems observed in the fossil record, characterized by a temporary collapse in biodiversity and an explosion of opportunistic species capable of surviving in the harsh conditions. The nuclear winter not only delayed ecological restoration, but also contributed to the extinction of approximately 75% of species existing at the time, including all non-avian dinosaurs. Its effects rippled across terrestrial, freshwater, and marine realms, synergizing with other environmental disasters triggered by the impact. In essence, the nuclear winter phase was a profound planetary-scale catastrophe induced by the asteroid impact. It demonstrates how interconnected Earth's systems are, how an astronomical event can disrupt the delicate balance of sunlight, temperature, and biological productivity, leading to widespread extinction. Understanding this dark chapter in Earth's history offers a somber reflection on the fragility of life when confronted with rapid and global-scale environmental change. It also informs contemporary studies on climate perturbations, atmospheric science, and the potential consequences of similar catastrophic events composing the broader narrative of Earth's ever-changing biosphere. As we move forward, the story continues by examining the related aftermath environmental stresses such as acid rain and ocean acidification, further layers on the complex extinction tapestry that sealed the fate of the dinosaurs and many other forms of life. Following the global darkness and plunging temperatures of the nuclear winter, the Earth endured yet another severe environmental assault: acid rain and ocean acidification. These phenomena further compounded the devastation wrought by the Chicxulub impact, triggering widespread biological stress that contributed significantly to the mass extinction of the late Cretaceous. When the asteroid collided with Earth's surface, it vaporized vast quantities of sulfur-rich rocks, releasing enormous volumes of sulfur dioxide, SO2, into the atmosphere. This sulfur dioxide mixed with water vapor to form sulfuric acid aerosols, leading to episodes of acid rain that fell worldwide. Unlike the smokestacks and pollution that cause acid rain today on a localized scale, these acid rain events were truly global and far more intense. This acidic precipitation had profound impacts on terrestrial and freshwater environments. Soils were leached of nutrients vital to plant growth, while direct contact with acidified rain devastated foliage and delicate seedling life. Freshwater habitats, such as lakes and rivers, experienced lowered pH levels, creating inhospitable conditions for many aquatic species, including amphibians, mollusks, and insects. The biological knock-on effects from reduced plant vigor and aquatic mortality cascaded through food webs, destabilizing ecosystems already weakened by the impact's earlier effects. In the oceans, acid rain and atmospheric changes triggered shifts in the chemistry of the seawater itself, intensifying ocean acidification. This process occurs when atmospheric carbon dioxide dissolves in seawater to form carbonic acid, decreasing the pH and altering carbonate chemistry. The addition of sulfuric aerosols and other volcanic gases from the impact likely accelerated these acidifying effects. Ocean acidification proved particularly catastrophic for marine organisms that relied on calcium carbonate to build shells and skeletons, including planktonic foraminifera, ammonites, corals, and some mollusks. Their shells dissolved or failed to form properly, weakening their populations and affecting the marine food web dramatically. Since many of these tiny organisms are foundational within ocean ecosystems, their loss propagated upward, undermining fish populations and marine reptiles. Moreover, acidification disrupted nutrient cycles in the oceans. Altered carbonate chemistry affected the solubility of minerals essential for marine life, while shifts in primary production, particularly the decline of photosynthetic plankton, diminished oxygen production and food availability. These changes contributed to episodes of hypoxia, or low oxygen zones, further stressing marine biodiversity. Fossil and geochemical evidence supports these conclusions. Sedimentary layers from the KPG boundary contain indicators of lowered pH, such as dissolution features in carbonate sediments and altered isotopic ratios of carbon and oxygen. Additionally, the disappearance or dramatic decline of acid-sensitive species in the fossil record heralds the severity of this environmental assault. The acidification, both atmospheric and marine, was rapid and severe enough that recovery for many species was greatly delayed. It synergized with other environmental stresses: the darkness, cooling, wildfires, tsunami disruption, and nutrient upheavals, creating a multifaceted crisis that few organisms could survive. Importantly, the impacts of acid rain and ocean acidification extended beyond immediate mortality. They reshaped the evolutionary trajectories of marine and terrestrial life, catalyzing shifts in biodiversity and community composition for millions of years after the extinction event. In this way, acid rain and ocean acidification were elemental components of the complex environmental feedback loops set in motion by the asteroid impact. They exemplify how chemical changes in Earth's atmosphere and oceans, driven by extraterrestrial forces, can cascade through ecosystems to precipitate a mass extinction. Continuing our exploration of the extinction event's profound impact, we next turn to the collapse of photosynthesis, the loss of the very energy foundation supporting life on land and in the sea. This sets the stage for an ecological famine that sealed the fate of many species and reshaped life on Earth for eons to come. As we journey further into the profound consequences of the Chicxulub impact, one of the most critical phenomena to understand is the collapse of photosynthesis, the process by which plants, algae, and photosynthetic plankton convert sunlight into energy, forming the foundational base of nearly all Earth's food chains. The asteroid's catastrophic effects, particularly the sunlight-blocking nuclear winter and subsequent environmental turmoil, caused a dramatic shutdown of this vital life-sustaining mechanism, triggering a cascade of ecological collapse, both on land and in the oceans. Photosynthesis depends fundamentally on the availability of sunlight, water, carbon dioxide, and suitable temperatures. In the moments to months following the impact, vast quantities of dust, soot, and aerosols filled the atmosphere, reducing sunlight penetration by up to 90% or more. This severe dimming deprived photosynthetic organisms of energy, effectively shutting down their metabolic functions and halting the synthesis of organic compounds essential for growth and reproduction. On land, the consequences were catastrophic. Forests, grasslands, and other plant communities withered under the extended darkness and pronounced cooling. Without sunlight, leaves could not generate energy, leading to widespread defoliation and plant death. In some regions, entire forests stood as skeletal remains, faded witnesses to a sudden ecological demise. The shutdown of photosynthesis caused a loss of oxygen production and the cessation of carbon fixation, disrupting atmospheric balance and accelerating climatic stresses. This vegetative collapse had immediate and severe impacts on herbivorous animals who depended directly on plants for sustenance. Herbivorous dinosaurs, including hadrosaurs and ceratopsians, faced starvation as their food sources dwindled inexorably. Consequently, carnivores feeding on these herbivores were simultaneously affected, precipitating a rapid cascade through terrestrial food webs. In freshwater ecosystems, aquatic plants and algae similarly faced diminished sunlight, leading to reduced oxygen production and habitat quality. The decline in photosynthetic aquatic vegetation disrupted the habitats of numerous amphibians, fish, insect larvae, and microorganisms, contributing to broader biodiversity loss. The oceans were perhaps even more dramatically affected. Phytoplankton, Microscopic photosynthetic organisms that drift among the ocean's surface waters form the base of marine food webs. These tiny organisms carry out roughly half of Earth's total photosynthesis today and are crucial for sequestering carbon dioxide. With sunlight obscured by the dust veil, phytoplankton populations collapsed. This, in turn, led to a near collapse of marine food chains. Zooplankton that feed on phytoplankton dwindled, followed by small fish and larger predators such as mosasaurs and plesiosaurs. The marine food pyramid, built upon the productivity of these primary producers, essentially crumbled. The reduction of photosynthesis also affected the global carbon cycle. Normally, plants and phytoplankton absorb carbon dioxide as they grow, but with their decline, atmospheric CO2 levels would have accumulated, contributing to greenhouse warming once the dust settled. Simultaneously, oxygen production plummeted, which may have exacerbated hypoxic or low oxygen conditions in marine environments, further stressing aquatic life. Fossil records provide compelling evidence for this photosynthetic collapse. Sedimentary layers from the KPG boundary exhibit sharp decreases in pollen and spore counts, indicating plant die-offs. Similarly, certain marine sediment deposits show dramatic reductions in calcareous planktonic fossils tied to photosynthetic organisms, coinciding precisely with the boundary layer. Moreover, the collapse of photosynthesis created a bottleneck effect on evolution and survival. Species capable of deriving energy through means other than photosynthesis, detritivores, scavengers, and deep-sea vent communities, managed to survive the crisis period better than strictly photosynthetic-dependent organisms. For instance, some hardy bacteria and archaea, as well as small mammals and avian dinosaurs that could exploit alternative food sources or habitats, had pockets of refuge. Recovery from this collapse was exceedingly slow, spanning thousands to millions of years. The replenishment of plant life on land depended on the gradual clearing of atmospheric dust and return of sunlight, while in the oceans, phytoplankton communities took extended periods to rebound, constrained by nutrient availability and changing ocean chemistry. This collapse also set the evolutionary stage for dramatic shifts in Earth's biota. The vacuum left by extinct species allowed for adaptive radiations among surviving groups. Flowering plants, which survived in limited capacities, would eventually diversify explosively in the Paleogene, reshaping terrestrial ecosystems. Similarly, small mammals, which had been minor players during the Mesozoic, proliferated and evolved to fill the niches vacated by dinosaurs. In sum, the shutdown of photosynthesis was a pivotal mechanism by which the asteroid impact precipitated mass extinction. By severing the vital flow of energy through ecosystems, it dealt a fatal blow to countless species and irrevocably altered the trajectory of life. As we advance, the story turns to the struggles faced by surviving terrestrial dinosaurs and other organisms grappling with the aftermath, illuminating the resilience and eventual decline of the last of the dinosaur giants. Emerging from the profound ecological upheavals triggered by the Chicxulub asteroid impact, terrestrial dinosaurs confronted an unprecedented struggle for survival. The immediate aftermath was brutal. The cataclysm had altered their world in fundamental ways, obliterating habitats, obliterating food sources, and transforming the climate. To understand how the non-avian dinosaurs met their demise, we must explore how they grappled with these challenges in the hours, days, and years following the impact. Before the impact, the terrestrial dinosaur communities were vibrant and diverse. Mighty herbivores such as Triceratops and Edmontosaurus roamed vast floodplains and forests, while apex predators like Tyrannosaurus rex reigned supreme. These ecosystems had thrived for millions of years, finely balanced with their food sources and environmental conditions. But the impact shattered this equilibrium. The first immediate threat to terrestrial dinosaurs was habitat destruction. The force of the impact and subsequent firestorms devastated landscapes over hundreds and potentially thousands of kilometers. Forests were incinerated, vegetation was stripped away or poisoned by acid rain. The collapse of photosynthesis disrupted the primary producers vital to herbivores, which in turn cascaded to carnivores dependent on these herbivores. Food scarcity emerged rapidly as a leading cause of stress and mortality. Herbivorous dinosaurs suffered as the lush plants they depended on died in the darkness and cold, while carnivores lost not only prey, but also faced competition with scavengers and smaller survivors able to exploit the devastated environment. The fragmentation of surviving populations into isolated refuges further inhibited the ability of species to recover. Physiological vulnerabilities compounded these ecological challenges. Dinosaurs, particularly large-bodied ones, were ectothermic or mesothermic, relying to varying degrees on external heat sources to regulate their body temperatures. The prolonged nuclear winter, with its plummeting temperatures and lack of sunlight, made thermoregulation increasingly difficult, especially for species accustomed to warm climates. Fossil evidence from the Hell Creek Formation and other late Cretaceous sites paints a somber picture. Just above the KPG boundary, dinosaur fossils become scarce, indicating a dramatic reduction in population sizes. Significantly, some studies suggest a pattern of decreased body size, Lilliput effect, where survivors demonstrated dwarfism, possibly an adaptive response to limited resources and environmental stress. Furthermore, reproductive challenges likely played a role. With vegetation gone and climates altered, nesting grounds and food for hatchlings would have been in short supply. Many dinosaur species probably failed to reproduce successfully, accelerating population declines. Not all dinosaur species faced extinction simultaneously. Evidence shows that some groups persisted slightly longer than others. For instance, ceratopsians and hadrosaurs seem to hang on until just before the boundary, while smaller theropods dwindled rapidly. Yet ultimately, none of the non-avian dinosaurs survived beyond the extinction horizon. The struggles were not only biological, but also ecological. Surviving species faced new pressures from an assortment of emerging competitors. Early mammals and birds adapted to exploiting niches in the devastated world. These survivors often had traits that enabled coping with harsh environments: smaller body sizes, endothermy, ability to regulate internal body temperature, varied diets, and reproductive strategies suited to unpredictable conditions. The extinction of non-avian dinosaurs unlocked vast ecological space. The disappearance of these dominant terrestrial vertebrates paved the way for mammals to diversify and radiate during the subsequent Cenozoic era. Yet, for the dinosaurs themselves, their profound struggle for survival was met with overwhelming environmental hostility that proved insurmountable. In sum, the aftermath of the asteroid impact forced terrestrial dinosaurs into a cascade of survival challenges: habitat annihilation, food shortages, climatic extremes, and biological constraints. Their evolutionary success across millions of years encountered an abrupt and irreversible wall, illustrating both the fragile interdependence of life and the sudden power of catastrophic global change. As we continue our exploration, we shall turn to the oceans to examine how marine life fared under these catastrophic conditions and the extinction cascades that unfolded beneath the waves. As we shift our focus from the terrestrial realm to the vast expanses of Earth's oceans, it becomes evident that the effects of the Chicxulub asteroid impact were equally, if not more, devastating beneath the waves. The marine ecosystems, which nurtured a diverse assemblage of life ranging from microscopic plankton to gigantic marine reptiles, suffered catastrophic declines and extinctions during this critical boundary period, reshaping ocean life for millions of years to come. Prior to the impact, the late Cretaceous seas were bustling with biodiversity. Reefs flourished with coral and rudist bivalves, planktonic organisms like foraminifera and calcareous nanoplankton thrived, and large marine reptiles such as mosasaurs, plesiosaurs, and ichthyosaurs dominated as apex predators. These interconnected ecosystems relied heavily on the productivity of photosynthetic plankton, which formed the base of the marine food web. The Chicxulub impact, however, triggered a series of immediate and long-term effects that fundamentally shattered these communities. One of the first consequences was the massive injection of dust and soot into the atmosphere, as we've discussed earlier, leading to the blocking of sunlight essential for photosynthesis. Phytoplankton populations, the microscopic plants responsible for nearly half of global photosynthesis, plummeted sharply due to this sunlight deprivation. A phenomenon documented clearly in the fossil record by an abrupt decline in their remains at the KPG boundary. This collapse of primary productivity starved higher trophic levels. Zooplankton, small fishes that fed on plankton, and large filter-feeding organisms all faced severe food shortages. The knock-on effects cascaded through marine food chains, resulting in a significant loss of biodiversity. Ammonites, once ubiquitous and diverse, showed a dramatic decline and finally disappeared completely along with many plankton taxa, indicating a profound biological crisis. Furthermore, acidification of oceans, triggered by increased atmospheric CO2 and sulfuric compounds released by the impact and associated volcanism, worsened these effects. Acidic waters compromised many calcifying organisms that depended on stable carbonate chemistry to build shells and skeletons. Corals suffered extensive reef collapse, affecting the complex habitats that many marine species depended upon. Another direct physical disturbance was caused by massive tsunamis generated by the impact. These megatsunamis ravaged shallow marine and coastal environments, destroying benthic communities and reshaping seafloor topography. Sediment deposits laden with marine fossils reveal sudden, chaotic burial of marine life, evidencing a violently disrupted ecosystem. Oxygen minimum zones in the oceans expanded dramatically due to the decomposition of dead organisms and altered circulation patterns, creating hypoxic or anoxic conditions, hostile to many aerobic marine creatures. This further restricted habitable zones, especially in continental shelf areas where much marine life resided. The cumulative effect of these disruptions was massive extinction across multiple marine groups. Estimates suggest that up to 75% or more of marine species were lost. Planktonic foraminifera saw the extinction of many genera, while reef-building corals underwent severe declines. Marine reptiles vanished entirely by the end of the Cretaceous, unable to withstand the collapse of their food supply and habitat. Numerous mollusks, echinoderms, and fish species also faced significant attrition. Despite the devastation, some marine lineages persisted through this extinction bottleneck. Certain benthic foraminifera, capable of surviving in low-oxygen environments, small opportunistic bivalves, and some fish groups like sharks endured. These survivors laid the foundation for marine ecosystem recovery that would unfold over millions of years in the Paleogene. Our understanding of marine extinctions at this boundary comes from global fossil records, examining microfossils in sediment cores, and from geochemical signatures indicative of marine environmental stress. These studies reveal both rapid extinction pulses and more prolonged phases of ecosystem collapse and recovery, highlighting the complexity of oceanic responses. In sum, the asteroid impact precipitated a marine mass extinction of unparalleled scale, erasing dominant Cretaceous species and driving a near-total reorganization of ocean life. The oceans, which had long been reservoirs of rich biodiversity, were rendered hostile to many inhabitants, and the cascading ecological collapse mirrored, with its own distinct dynamics, the terrestrial catastrophe. As we continue, it is essential to consider additional drivers beyond the initial impact, secondary killers such as prolonged volcanism and the Deccan Traps eruptions, which may have compounded the extinction effects both in marine and terrestrial realms, adding layers to this multifaceted global crisis. While the asteroid impact at Chicxulub is widely regarded as the primary trigger for the mass extinction at the close of the Cretaceous period, a growing body of research points to additional environmental stressors that compounded the catastrophic effects. Most notably, the massive volcanic eruptions of the Deccan Traps in what is now India. These vast outpourings of basaltic lava, occurring over hundreds of thousands to millions of years, played an equally profound and complex role as secondary killers in shaping the extinction landscape. The Deccan Traps represent one of the largest volcanic provinces on Earth, covering an expanse exceeding 500,000 square kilometers. Formed by successive enormous lava flows, these eruptions released prodigious quantities of volcanic gases, including carbon dioxide, CO2, sulfur dioxide, SO2, and other aerosols. These gases had far-reaching effects on climate, atmospheric chemistry, and oceanic environments, effects that could be both long-term and acute. Geochronological studies using high-precision radiometric dating have refined the timeline of Deccan volcanism, showing that significant eruptive phases coincided closely with the end Cretaceous extinction interval, occurring both just prior to and after the Chicxulub impact. This temporal overlap raised critical questions. Did the volcanism exacerbate environmental stresses already triggered by the impact? Could volcanic gases have initiated climatic alterations that weakened ecosystems, rendering them more vulnerable to extinction? Contemporary scientific consensus suggests that the answer is likely yes. Volcanic emissions of CO2 contributed to greenhouse gas buildup, slowly warming the planet over thousands of years before and after the impact. This gradual warming would have imposed physiological stresses on many species adapted to stable climates, potentially disrupting reproductive cycles, food availability, and habitat suitability. On the other hand, sulfur dioxide released in massive quantities created sulfate aerosols in the stratosphere, which reflected sunlight and caused episodic cooling or volcanic winters. The interplay between warming and cooling cycles led to environmental instability, with repeated fluctuations in temperature and precipitation. These volatile climatic oscillations strained marine and terrestrial ecosystems. Acid rain from volcanic SO2 damaged plant life and aquatic habitats, contributing to the breakdown of food chains. Ocean acidification, driven both by volcanic CO2 and asteroid-derived chemical changes, further compromised marine calcareous organisms, compounding the extinction pressure. Volcanism also altered atmospheric composition through heavy injection of particulates and potentially increased atmospheric dust loads, enhancing the sky-darkening effects already initiated by the impact ejecta. This prolonged reduction in sunlight perpetuated the suppression of photosynthesis, retarding ecological recovery. Importantly, the Deccan eruptions persisted for hundreds of thousands of years after the extinction event, influencing Paleogene climate fluctuations and ecosystem evolution. This prolonged volcanic activity likely slowed the post-extinction rebound of biodiversity, shaping early mammalian and avian diversification. Recent research employing geochemical proxies, climate modeling, and precise stratigraphic correlation underscores the significance of volcanism as both a prelude and aftermath to asteroid catastrophe. It reveals a synergistic scenario where gradual volcanic stress primed ecosystems. The asteroid impact delivered a sudden, dramatic blow, and subsequent volcanism impeded recovery, together orchestrating a complex extinction narrative. In synthesizing these findings, it becomes evident that the mass extinction was not a solitary event, but a multifaceted crisis involving intersecting geological and extraterrestrial forces. The Deccan Traps volcanism therefore stands as a crucial secondary killer, enriching our understanding of Earth's dynamic and sometimes devastating environmental history. As we turn next to delineating the detailed timeline, the days, months, and years during which these transformational processes played out, we will further appreciate the intricate choreography of destruction and recovery that defined this pivotal moment in Earth's story. To truly grasp the magnitude of the dinosaur extinction event, it's essential to explore the timeline that unfolds in the critical days, months, and years following the asteroid impact, an interval when Earth underwent rapid and profound transformations. This temporal reconstruction, pieced together through geology, paleontology, geochemistry, and computer modeling, helps us understand how the initial cataclysm translated into a mass extinction and ecological upheaval. The story begins at the very moment of impact, approximately 66 million years ago. Within seconds, the asteroid struck with unimaginable force, creating a crater roughly 150 to 180 kilometers in diameter at Chicxulub. The immediate blast vaporized everything in the vicinity, including vast tracts of forest, coastal environments, and countless organisms. Shockwaves radiated in all directions, triggering near instantaneous destruction within hundreds of kilometers. Minutes after impact, a global rain of molten rock and debris, ejecta, descended through the atmosphere. This sparked widespread wildfires, as re-entering glass spherules heated the lower atmosphere sufficiently to ignite vegetation across continents simultaneously. Soot-rich sediment layers around the world attest to this intense and synchronous burning. Simultaneously, powerful megatsunamis inundated coastlines surrounding the impact site, and then, with less intensity, across distant continental margins. Sedimentary deposits rich in chaotic mixtures of marine and terrestrial material are found as geological signatures of these giant waves. Within hours to days, intense dust and soot clouds filled the stratosphere. These dense particulates drastically reduced the amount of sunlight reaching Earth's surface, plunging the planet into darkness and cold. This nuclear winter phase lasted for months to years, impeding photosynthesis, collapsing ecosystems, and triggering a cascade of extinctions that reverberated through terrestrial and marine food webs. In the weeks and months following the impact, acid rain fell globally, a byproduct of sulfur dioxide and other gases injected into the atmosphere both by the impact and contemporaneous volcanic activity. Acidic precipitation damaged plant life and freshwater ecosystems, compounding environmental stress. For years after, climate oscillated between cooling from aerosols still in the atmosphere and warming due to elevated carbon dioxide released by impact-related fires, vaporized carbonate rocks, and erupting volcanoes, including the Deccan Traps. These competing effects caused fluctuating environmental conditions, challenging survivors' adaptability. Fossil records from sediment layers directly above the impact boundary indicate a rapid and widespread loss of species within a geologically instantaneous window, equivalent to thousands of years or less, supporting the suddenness of the extinction. Over the following decades to millennia, ecosystems were impoverished. Opportunistic species, typically small-bodied and rapidly reproducing organisms like certain mammals, birds, insects, and plants, gradually colonized the barren landscapes. Marine ecosystems similarly shifted towards dominance by more resilient or generalist species. Only after tens of thousands to hundreds of thousands of years did signs of ecological stabilization and increasing complexity emerge. This marked the slow recovery phase when new evolutionary radiations began to fill niches vacated by extinct taxa. Modern scientific techniques, including high-precision radiometric dating, isotopic analyses, and sedimentology, allow ever more detailed resolution of this interval, making the extinction event one of the most intensively studied transitions in Earth's deep history. Ultimately, the timeline of the extinction event illustrates a narrative of initial instantaneous catastrophe, followed by prolonged environmental upheaval and recovery. A sequence shaped by interlinked geological, atmospheric, and biological processes. Understanding this chronology gives vital insight into how sudden cosmic violence intersected with Earth's systems to dramatically alter the trajectory of life on our planet. As we proceed, the next chapter will delve into the immense death toll cataloged by scientists, quantifying the species lost and further illuminating the profound biospheric consequences of this global extinction event. The fatal day when the Chicxulub asteroid struck Earth cast a shadow that stretched far beyond immediate destruction. It ignited a series of ecological collapses that led to one of the most profound episodes of biodiversity loss in our planet's history: the Cretaceous Paleogene, KPG, mass extinction. To comprehend the scale of this biological cataclysm, scientists have meticulously cataloged species lost across terrestrial, marine, and aerial realms to paint a sobering picture of the death toll and its enduring impact. Prior to the extinction event, Earth was home to an astonishing diversity of life forms. The late Cretaceous period saw flowering plants diversifying, complex insect communities flourishing, abundant amphibians, early mammals beginning to carve out their roles, and, of course, the titan dinosaurs ruling terrestrial ecosystems. The oceans brimmed with myriad ammonites, marine reptiles such as mosasaurs and plesiosaurs, schooling fishes, and vast populations of planktonic microorganisms critical to the food web. The extinction event, however, wrought devastation that was swift and widespread. Estimates suggest that approximately 75% or more of all species on Earth perished during this interval, with many higher taxonomic groups experiencing near-total losses. Among the most iconic casualties were the non-avian dinosaurs. All large terrestrial dinosaurs, be they the towering sauropods, the horned ceratopsians, the duck-billed hadrosaurs, or the fearsome theropods like Tyrannosaurus rex, disappeared without exception. Their fossil record ends abruptly at the KPG boundary. This total loss signified the end of an era and opened ecological niches that mammals and birds would later fill. Marine life also suffered an unparalleled extinction. Ammonites, which had thrived for hundreds of millions of years, were completely wiped out. Marine reptiles, mosasaurs, plesiosaurs, and ichthyosaurs vanished as well, erasing the apex predators of the seas. Planktonic foraminifera experienced a severe bottleneck, with nearly half their genera lost, profoundly disrupting the marine food web's bedrock. Reef ecosystems collapsed extensively because corals and rudest bivalves, vital reef builders, also faced steep declines. On the botanical front, many specialized flowering plants and gymnosperms saw drastic reductions. Pollen and spore records indicate a marked decrease in diversity, reflecting the collapse of forested habitats and ground cover. This plant loss cascaded through herbivorous insect communities and their predators, resulting in secondary extinction waves. Small mammals, early birds, avian dinosaurs, amphibians, certain reptiles, and hardy invertebrates like cockroaches and freshwater bivalves displayed varying resilience, with some lineages persisting across the boundary. However, even among survivors, species richness dwindled, and genetic bottlenecks likely occurred, setting the stage for evolutionary radiations in the aftermath. The death toll catalog is not merely a tally of vanished species, it reflects profound shifts in evolutionary trajectories. Entire families and orders were extinguished, fundamentally altering life's blueprint. The ecological vacuums created by this mass mortality eventually facilitated the rise of mammals and modern birds, but only after protracted periods of recovery. Scientists reconstruct this catalog through an interdisciplinary approach, analyzing fossil assemblages worldwide, employing radiometric dating to pinpoint extinction horizons, studying trace fossils and microfossils for subtle extinction signals, and integrating geochemical markers that denote environmental stress. This monumental effort continues to refine our understanding of the extinction's breadth and complexity. This comprehensive census of life lost underscores the vulnerability of Earth's biosphere to rapid, high-magnitude disturbances. It serves as a poignant reminder of how intimately connected species' survival is to stable environmental conditions, and how an extraterrestrial event could irreversibly reshape biological history. With this understanding of the sheer scale and significance of life lost, our next exploration will address the mysteries of survival, unraveling why some species endured the cataclysm while others perished, revealing the traits and circumstances that determined their fates. Amidst the catastrophic mass extinction that closed the Cretaceous period and extinguished the reign of the non-avian dinosaurs, a critical and fascinating question arises. Why did some species survive while so many others were wiped out? This question leads us into the study of resilience and adaptation in a time of unprecedented global crisis. Particularly, it shines a spotlight on the ancestors of today's birds, mammals, and certain reptiles, groups that managed to endure the tumultuous environmental upheavals that spelled doom for the majority of Earth's inhabitants. Firstly, it is essential to recognize that survival during such an extinction event hinged on a combination of biological, ecological, and physiological traits. Species that possessed qualities enabling them to persist through the prolonged darkness, reduced food availability, climatic oscillations, and toxic environmental conditions were more likely to endure. This selective survival underscores the interplay between adaptability and circumstance. Birds stand as the direct descendants of small theropod dinosaurs and are the sole surviving dinosaur lineage. The avian survivors were predominantly small-bodied, feathered creatures capable of flight or gliding, with high metabolisms allowing better thermoregulation. Their ability to fly afforded them mobility to escape deteriorating habitats and exploit diverse food resources, from seeds to insects to small vertebrates. Moreover, birds' nesting behaviors, which included brooding and possibly some level of parental care, may have increased offspring survival during harsh conditions. Their generalized omnivorous diets allowed flexibility when traditional food chains were disrupted, a crucial advantage when plant and prey species became scarce. Additionally, their relatively rapid reproductive cycles likely aided quick population recovery once environmental conditions stabilized. Mammals, mostly small at the end of the Cretaceous, were predominantly nocturnal, burrowing, or semi-fossorial animals. These lifestyle traits provided refuges from the surface-level devastation caused by firestorms, acid rain, and temperature fluctuations. Being endothermic, mammals could maintain internal body temperatures independent of environmental extremes, an advantage during the prolonged darkness and cooling of the nuclear winter phase. Their diets were varied, with many species capable of exploiting insects, seeds, and detritus, food sources that persisted better than large plants or animals. The flexibility in feeding and behavior, combined with small body size and high reproductive rates, contributed significantly to their survival. Mammalian burrowing also likely shielded them from the initial blast effects and subsequent environmental toxins. Certain reptiles, including turtles, crocodilians, and lizards, also persisted through the extinction event. Many reptiles share a physiological trait of ectothermy, but can survive in aquatic environments or burrows where environmental extremes were buffered. Aquatic turtles and crocodiles, for instance, could exploit water bodies less affected by atmospheric particulates and acid rain, and often possess hardy physiologies, enabling survival in low oxygen or variable conditions. Additionally, many reptiles exhibit slow metabolisms and can survive prolonged periods of starvation or low activity, affording resilience in post-impact food-scarce ecosystems. Their reproductive strategies, including egg-laying in protected environments and capacity for dormancy in harsh conditions, provided further survival advantages. Importantly, many surviving species were generalists rather than specialists. Ecological generalists, which can utilize a range of habitats and dietary resources, generally outperform specialists during times of environmental stress. Survival favored adaptability and flexibility over highly specialized niches. Fossil evidence supports these survival patterns. Small-bodied birds and mammals emerge in strata above the KPG boundary, indicating their persistence. Some reptiles show continuity across the boundary with minimal morphological disruption. Contrastingly, the extinction of large-bodied and specialist taxa reflects their vulnerabilities. Moreover, molecular and genetic studies indicate that some lineages experienced population bottlenecks but retained sufficient genetic diversity to radiate and diversify in the aftermath. This genetic resilience further underpinned the evolutionary success of these groups post-extinction. The survival of birds, mammals, and certain reptiles after one of Earth's most severe mass extinctions reveals the profound influence of biological characteristics in overcoming global catastrophes. Their stories are testimonies of adaptability, ecological opportunism, and physiological versatility. Understanding these survival mechanisms provides not only insights into past extinction events, but also valuable perspectives on modern conservation challenges. It highlights how traits such as dietary flexibility, habitat breadth, reproductive strategies, and physiological resilience can determine the fate of species faced with rapid environmental change. As we proceed, the fossil record will shed more light on the final chapters of the last non-avian dinosaurs and the dawn of new evolutionary horizons that shaped the modern biosphere. In the silent layers of rock that chronicle our planet's deep history lie the remnants of Earth's final non-avian dinosaurs, fossils that offer poignant testament to their last days on a world dramatically altered by cataclysm. These fossils unlock stories of survival, struggle, and ultimate demise, providing crucial clues about the timing, distribution, and nature of the dinosaur extinction event. The fossil record of the late Cretaceous, especially from well-studied formations such as the Hell Creek Formation in North America, the Meverano Formation in Madagascar, the Lancian faunas in South America, and sites in Asia and Europe, gives a window into the last assemblages of dinosaurs before their abrupt disappearance. These formations, rich in sedimentary deposits spanning the KPG boundary, preserve bones, tracks, and sometimes fragile impressions of feathers and skin. They illuminate the diversity of species that thrived until the very end, including iconic genera like Tyrannosaurus rex, Triceratops, Edmontosaurus, and many more. The fossil layers immediately below the KPG boundary teem with abundant dinosaur remains, signaling vibrant populations coexisting in diverse habitats. Herbivorous dinosaurs, such as the hadrosaurs and ceratopsians, are often found in large numbers, hinting at flourishing herbivore herds. At the same time, carnivorous theropods, including young and subadult individuals, appear in a variety of growth stages, suggesting ongoing reproductive success up until the boundary. However, direct above these layers, corresponding to the boundary clay enriched with iridium, the fossil record turns starkly barren of non-avian dinosaur remains. This abrupt transition encapsulates the extinction moment. No dinosaur fossils are definitively found above this layer, marking a sudden end rather than a gradual decline. This terminal pattern supports a catastrophic extinction linked to the asteroid impact rather than slow attritional processes. Intriguing evidence also comes from microfossils and trace fossils. For instance, a sharp decline in pollen, spores, and dinosaur eggshell fragments above the boundary suggests disruptions in reproductive cycles and vegetation. Some suggest a brief post-extinction survival of a few dinosaur species in refugia, but the consensus remains that no non-avian dinosaurs endured beyond this interval. Recent advances in radiometric dating and geochemical analyses have refined the timeline of these fossil deposits to within thousands, possibly hundreds of years. A fleeting moment in geological terms, underscoring the rapidity of extinction. The presence of soft tissue impressions and feathered theropod fossils preceding the boundary enhances our understanding of the biology and behavior of the last dinosaurs. These findings reveal sophisticated sensory structures, social behavior, and nesting habits, painting a picture of dynamic creatures caught in Earth's final upheaval. Additionally, fossils from different continents show regional variation, indicating that some dinosaur groups persisted longer or were more abundant in certain locales, yet all ultimately succumbed. This biogeographical complexity adds depth to extinction narratives, reminding us that Earth's ecosystems were intricately connected yet locally distinct. These fossilized remains not only chronicle extinction, but also function as a bridge to post-extinction life, providing comparative baselines for studying survivorship and evolutionary radiations of mammals and birds. Studying the last dinosaurs through their fossils encapsulates a profound moment of planetary change, where ancient giants teetered on extinction's edge, leaving behind a legacy etched in stone, waiting to tell their final story to a new epoch. As we proceed, the investigative tools scientists employ to reconstruct these final days will shed further light on this pivotal chapter in Earth's saga. Unlocking the mysteries of the dinosaurs' final days requires a multidisciplinary approach, combining paleontology, geology, chemistry, and cutting-edge technologies. Scientists aim to reconstruct not merely a broad picture of extinction, but the sequence of events, hour by hour, day by day, that culminated in the demise of the non-avian dinosaurs. This quest to piece together Earth's deep past is both complex and fascinating, drawing upon fossil evidence, sediment analysis, radiometric dating, and computer simulations. Central to this endeavor is the KPG boundary layer, a thin geological stratum found worldwide that serves as a timestamp marking the extinction event. This boundary is distinguished by its anomalously high concentration of iridium, a metal more common in asteroids than Earth's crust, supporting the asteroid impact hypothesis. By examining this layer's composition, thickness, and surrounding sediments, researchers have gained insights into the environmental chaos that unfolded. High-precision radiometric dating techniques, such as uranium lead dating, allow scientists to date volcanic ash layers and impact glass spherules with remarkable accuracy, confining the timing of the extinction to a narrow window. These techniques reveal that the demise of many species occurred abruptly, aligning with the fallout from the Chicxulub impact. Fossil beds like the Hell Creek Formation provide snapshots of ecosystems just before and after the impact. Detailed stratigraphic studies illustrate a sudden absence of non-avian dinosaur remains immediately above the boundary, concomitant with changes in plant pollen, freshwater microfossils, and charcoal layers from global wildfires. These fossils, combined with geochemical signatures such as isotopic anomalies, indicate swift environmental deterioration. Microscopic analysis reveals the presence of shocked quartz and microtectites, tiny glass beads formed by molten rock vaporization during the impact, within boundary sediments. These provide direct physical evidence of the impact's violence and aid in correlating global sites. Additionally, sedimentary structures indicate tsunami deposits and rapid burial, reflecting geological upheavals. Environmental proxies such as stable isotope ratios, carbon, oxygen, sulfur, extracted from fossil shells and sediments, track abrupt climatic changes. Shifts in isotopic values highlight temperature drops, ocean acidification, and disruptions in carbon cycling consequent to the impact and associated volcanism. Recent advances in synchrotron microscopy and computed tomography have enabled non-destructive examination of microscopic fossils and bone microstructures. This has revealed growth patterns, health status, and even signs of stress in organisms leading up to extinction, offering a window into their final life conditions. Computer models simulate atmospheric dust dispersal, firestorm intensity, climate perturbations, and ecological impacts. Integrating these models with physical evidence creates a dynamic timeline of how sunlight was blocked, temperatures dropped, and food webs collapsed. Fossilized pollen and spores provide insight into vegetation shifts, showing which plant groups persisted longer and which declined rapidly. Similarly, microfossils of marine plankton track oceanic ecosystem collapses. Together, they detail the breakdown and slow rebuilding of ecosystems. Moreover, studies of dinosaur nesting sites and bone beds reveal behavioral changes potentially linked to environmental stress, such as altered reproductive timing or population density fluctuations during final generations. This comprehensive scientific tapestry, woven from diverse data strands, continues to refine our understanding of the last days on Earth before the dinosaurs vanished. Each discovery enriches our knowledge of the catastrophic mechanisms, survival challenges, and immediate aftermath of the impact. By reconstructing these final days in meticulous detail, science not only honors the legacy of the dinosaurs, but also highlights the interplay of cosmic and terrestrial forces in shaping life's evolution. This understanding lays the groundwork for the subsequent return and diversification of life in the aftermath, an enduring testament to resilience amid extinction. As the narrative unfolds, the next segment will explore how life rebounded following the devastation, evolving and radiating in novel ways to populate the transformed world of the Cenozoic. After the devastating extinction event that marked the end of the Cretaceous period, Earth entered a profound period of ecological vacuum and transformation. This epoch, often referred to as the dawn of the Cenozoic era, set the stage for the remarkable rebound of life, a resurgence characterized by evolutionary innovation, diversification, and the filling of ecological niches left vacant by the vanished dinosaurs and countless other species. This chapter of Earth's history is best described by the concept of adaptive radiation, where lineages rapidly diversify and adapt in response to new opportunities and challenges. With the dominant non-avian dinosaurs gone, the planet's ecosystems were suddenly void of many large vertebrate competitors and predators. This absence created opportunities for survivors, mammals, birds, reptiles, and myriad invertebrates to exploit unoccupied niches. The recovery of life was neither instantaneous nor uniform, but involved a complex interplay of environmental stabilization, climatic shifts, and biological evolution over millions of years. Mammals, which had existed in the shadows of dinosaur dominance for over 100 million years, rapidly expanded in size, diversity, and ecological roles. Early small, generalized mammals gave rise to a wealth of forms: herbivores, carnivores, omnivores, and aquatic species, colonizing forests, grasslands, and aquatic habitats. From tiny shrew-like creatures to formidable herbivorous ungulates and apex predators, mammals embarked on a trajectory that would eventually lead to the rich tapestry of modern mammalian life. Birds also flourished in this new era. Freed from the competition and predation pressures posed by large theropods, birds diversified into a vast array of niches. Some evolved specialized beaks and behaviors, occupying roles akin to mammals on land, while others became adept at soaring and exploiting open skies and new environments. These evolutionary innovations paved the way for most of today's avian diversity. In marine ecosystems, similar adaptive radiations occurred following the collapse of many Cretaceous marine groups. New species of fish, marine mammals such as early cetaceans, and invertebrates adapted to the transformed oceans. Coral reefs, devastated by the extinction event, gradually recovered, providing habitats for diverse marine life. The cycling of nutrients and energy through marine ecosystems stabilized, supporting a vibrant and dynamic ocean biosphere. Plant life rebounded as well. Flowering plants, which had begun diversifying during the late Cretaceous, expanded rapidly, reshaping terrestrial landscapes. Forests, grasslands, and wetlands became more complex, facilitating new interactions between plants, pollinators, herbivores, and decomposers. This botanical resurgence supported the evolving animal communities, adapting to newly available food sources and habitats. Underlying these adaptive radiations were genetic and developmental innovations that allowed surviving lineages to exploit diverse environments and evolve novel traits. Changes in genomic organization, reproduction strategies, and physiological adaptations conferred advantages in fluctuating climates and disturbed habitats. Fossil evidence bears witness to these evolutionary rebounds. Newly diversified mammal faunas in the Paleocene and Eocene, the first appearances of many modern bird groups, and the gradual replacement of some marine reptiles with marine mammals narrate a story of life's resilience and creativity. Importantly, this era also featured profound climatic and geological changes, including the formation of mountain ranges, shifts in ocean currents, and global temperature fluctuations, all of which influenced evolutionary pathways. Adaptive radiations did not occur in isolation, but were shaped strongly by Earth's changing environment. Studying the return of life after the mass extinction reveals fundamental patterns of evolution and ecology. How life responds to catastrophe, the conditions fostering innovation, and the intricate dance between organisms and environment that drives biodiversity. This rebirth of life following near annihilation ultimately paved the way for the rich, complex biosphere we inhabit today. It transformed Earth from a world dominated by reptiles to one shaped by mammals, birds, and flowering plants, a legacy rooted deeply in the evolutionary processes that followed the greatest extinction event of the dinosaurs. While the asteroid impact hypothesis centered on the Chicxulub crater has gained widespread acceptance as the principal cause of the mass extinction event at the end of the Cretaceous period, the scientific narrative is neither singular nor static. Over decades, alternative and complementary theories have been proposed, debated, and refined, an ongoing process that underscores the complexity of Earth's history and the multifaceted nature of extinction dynamics. One of the earliest alternative hypotheses focused on prolonged and intense volcanic activity as the driver of extinction. The Deccan Traps, massive volcanic province in present-day India, emitted vast quantities of lava, carbon dioxide, sulfur dioxide, and other gases around the KPG boundary. Advocates of this theory argue that sustained volcanic eruptions created greenhouse warming, acid rain, and ocean acidification over extended periods, gradually destabilizing ecosystems and precipitating extinctions. Some studies suggest that these volcanic effects overlapped and perhaps amplified the impact-related stresses. Another proposed factor involves significant sea level changes and associated habitat fragmentation. Fluctuating sea levels during the late Cretaceous could have altered coastal and shallow marine environments, critical to many species. Habitat loss and ecological isolation might have contributed to fading biodiversity prior to the extinction pulse. Climate variability, independent of catastrophic events, also features in some interpretations. Changes in temperature gradients and regional climates could impose selective pressures over longer timescales, potentially eroding populations' resilience. Some paleontologists introduced hypotheses emphasizing gradual and complex biotic interactions, including competition, disease, or invasive species dynamics as contributors to extinction patterns. Others explore the potential for impact-triggered phenomena such as global wildfires or oceanic anoxia, oxygen depletion, to act synergistically. The debate extends to the timing and sequence of extinction pulses. Analyses of fossil records sometimes suggest multiple extinction events over hundreds of thousands of years, rather than a single instantaneous die-off. This perspective adds nuance to understanding extinction as a prolonged crisis rather than an abrupt catastrophe. These alternative theories often do not outright reject the asteroid impact hypothesis, but seek to integrate it within a multifactorial framework. This comprehensive view acknowledges that Earth's biosphere is influenced by a suite of geological, climatic, and biological processes that intertwine. Advances in dating methods, geochemical proxies, and more precise stratigraphic correlations continue to refine timelines and environmental reconstructions, helping to clarify these controversies. Emerging evidence increasingly supports a model where the asteroid impact served as a critical trigger within a backdrop of environmental stresses, including volcanism and climate shifts. Scientific discourse around these theories exemplifies the dynamic and self-correcting nature of research. Through continued interrogation of evidence, debate, and technological progress, our understanding of the KPG extinction grows richer and more sophisticated. Exploring these alternative perspectives deepens our appreciation of Earth's intricate systems and the multitude of factors that can drive life's ebbs and flows. As we move forward, the legacy of the dinosaurs and the long-term influence of the extinction event on Earth's future become clearer, connecting past upheavals to present and future challenges faced by life on our ever-changing planet. The extinction of the non-avian dinosaurs approximately 66 million years ago was a profound turning point, not only ending one chapter of Earth's biological history, but also setting the stage for the planet's future trajectory in remarkable ways. The legacy of the dinosaurs extends far beyond their reign and dramatic demise. It encompasses the reshaping of ecosystems, evolutionary pathways, and even Earth's climate and geology, all of which have profoundly influenced the biosphere we inherit today. The immediate consequence of their extinction was the opening of ecological niches that had long been held by these dominant reptiles. With the colossal herbivores and apex predators vanished, mammals, some birds, reptiles, and other forms of life were freed from intense competition and predation pressures. This ecological vacuum triggered a remarkable burst of evolutionary diversification known as an adaptive radiation. Mammals expanded into diverse forms, evolving into the ancestors of rodents, primates, carnivores, and many other groups. Birds flourished, giving rise to virtually all modern avian lineages. This sweeping diversification fundamentally reshaped terrestrial ecosystems, paving the way for complex forest systems, grasslands, and richer food webs. Furthermore, the loss of large dinosaurs altered nutrient cycling and vegetation dynamics on land. Herbivorous dinosaurs had a significant impact on plant communities, influencing forest composition and structure. Their absence allowed new plant groups, especially flowering plants, to flourish in different ways, altering the patterns of herbivory and pollination that drive ecosystem development. These botanical changes contributed to shaping climates and habitats in profound feedback loops. In marine environments, the extinction reshaped predator-prey relationships and biodiversity patterns. The disappearance of large marine reptiles made room for the rise of marine mammals like whales and dolphins, which would eventually claim top predator roles in the oceans. Coral reef systems and benthic communities underwent reorganization, with modern coral groups eventually replacing many extinct Cretaceous species. This transition influenced ocean chemistry and food chain dynamics for millions of years thereafter. Geologically, the extinction event and its aftermath also influenced sedimentation patterns, bioturbation, how organisms disturb sediments, and even atmospheric compositions. The impacts of massive fires, volcanic eruptions, and the shift in vegetation altered carbon cycling, which in turn affected Earth's climate trajectories through the Paleogene and beyond. Culturally and scientifically, the dinosaurs have left an indelible impression on human imagination and inquiry. Their extinction spurred critical advancements in geology, paleontology, and evolutionary biology, driving a deeper understanding of Earth's processes and life's vulnerability to rapid environmental change. The story of the dinosaurs' rise and fall cautions us about the fragility of ecosystems and the potential consequences of sudden global disturbances. Today, the reverberations of the dinosaur extinction inform conservation biology and climate science, highlighting the importance of biodiversity and the risks posed by anthropogenic changes. The legacy of the dinosaurs reminds us that extinction is a natural, yet sometimes abrupt and devastating force, urging us to steward Earth's remaining life with care. In essence, the extinction of the non-avian dinosaurs was both an end and a beginning, terminating the reign of one great lineage and catalyzing the emergence of another, setting the course for the rich and diverse biosphere we call home. This legacy intertwines biological evolution, geological change, and human understanding into a continuing story of life on a dynamic planet. The mass extinction that ended the age of dinosaurs stands not only as a monumental event in the annals of Earth's natural history, but also as a profound lesson for humanity today. Understanding this cataclysmic episode offers us invaluable insights into the fragility and resilience of life, the delicate balance of ecosystems, and the consequences when that balance is disrupted on a global scale. The human connection to such mass extinctions is deeply significant, as it reflects both our origins and our responsibilities as stewards of the modern biosphere. First and foremost, the study of ancient mass extinctions, especially the one that closed the Cretaceous period, reveals that life on Earth has been repeatedly shaped and reshaped by sudden and often violent environmental changes. These insights underscore that biodiversity, while incredibly rich and diverse, is not invulnerable. Past extinctions demonstrate how swiftly complex ecosystems can unravel when fundamental environmental drivers, climate, atmospheric chemistry, ocean conditions, are abruptly altered. For humans, who thrive in an interconnected and interdependent world, these patterns are a stark warning. Our industrial activities increasingly impact the planet's climate, land use, atmospheric composition, and biodiversity, echoing some of the stresses that preceded ancient extinctions. By studying the geological record and fossil evidence, we recognize that rapid environmental changes often overwhelm species' abilities to adapt or migrate, leading to elevated extinction rates. This understanding frames the current biodiversity crisis and Anthropocene epoch within the broader context of Earth's natural history, amplifying the urgency of conservation and sustainable practices. Moreover, mass extinction research teaches us about the mechanisms of recovery and resilience. The way life rebounded after the dinosaurs' extinction, through evolutionary radiations, ecological innovation, and the emergence of new dominant groups demonstrates nature's capacity for renewal given time and stable conditions. However, it also highlights that such recoveries span millions of years, far beyond the timescales relevant to human civilization. This gap amplifies the responsibility we hold to prevent irreversible loss and to maintain ecological integrity. Mass extinctions also deepen our appreciation for the interconnectedness of life. The asteroid impact triggered fires, atmospheric changes, acid rain, ocean acidification, and daylight blocking, effects that cascade through the Earth's systems, influencing terrestrial and marine life alike. Such complexity reminds us that environmental issues cannot be viewed in isolation. Changes in one domain propagate throughout the biosphere. From a scientific perspective, the human fascination with dinosaurs and their extinction has driven significant advances in geology, paleontology, climatology, and planetary science. This interdisciplinary inquiry expands our knowledge of Earth's history and even cosmic hazards. The asteroid impact theory, born from clues in iridium layers, pioneered new ways of integrating extraterrestrial events into Earth sciences, highlighting threats that could repeat. Culturally, the dinosaur extinction story permeates human imagination through literature, art, education, and media, serving as a powerful symbol of change, loss, and the passage of time. It provokes reflection on humanity's place in nature and our stewardship obligations toward the environment. Understanding mass extinctions enriches our dialogue about sustainability, environmental ethics, and global change. It encourages proactive measures in biodiversity conservation, climate action, and disaster preparedness. Recognizing patterns from deep time informs decisions that influence our planet's future, emphasizing prevention over reaction. In essence, the human connection to mass extinctions links past devastation with present challenges and future possibilities. By learning from Earth's ancient crises, we gain perspective on the responsibilities and choices we face today, striving to ensure that life, in all its remarkable diversity, endures well beyond our own time. The catastrophic extinction event that eradicated the non-avian dinosaurs over 66 million years ago remains a powerful reminder to humanity of the fragile balance underpinning life on Earth. Yet, far from being a distant historical anecdote, the echoes of that ancient catastrophe reverberate today, resonating as urgent warnings about modern threats to biodiversity and planetary health. As we face unprecedented environmental changes, understanding these parallels is vital to guiding scientific knowledge and societal action in the present era. One of the most alarming echoes lies in the ongoing loss of species, often termed the sixth mass extinction. Current extinction rates are estimated to be hundreds to thousands of times higher than natural background rates, driven largely by human activities such as habitat destruction, pollution, climate change, overexploitation, and invasive species introduction. Unlike the abrupt asteroid impact event, this extinction crisis unfolds over decades and centuries, but its trajectory threatens comparable biodiversity loss. Modern threats also mirror the environmental disruptions following the asteroid impact. Climate change, driven by elevated greenhouse gases analogous to those released by both volcanic activity and asteroid impact-induced fires, is altering habitats globally. Rising temperatures, shifting rainfall patterns, acidification of oceans, and extreme weather events undermine ecosystem stability, much like the ancient nuclear winter and acid rain once did. Scientists issue warnings based on extensive research into Earth's past extinction events, including the KPG catastrophe. These natural experiments provide insight into how ecosystems respond to rapid environmental change, the cascading effects on food webs, and thresholds beyond which recovery becomes arduous or impossible. This knowledge underscores the importance of mitigating current impacts to avoid irreversible losses. Asteroid detection and planetary defense initiatives, inspired partly by the realization that cosmic impacts can reshape life on Earth, now occupy a vital role in safeguarding the planet. Efforts to monitor near-Earth objects seek to provide early warning and potential means to avert future impact disasters, highlighting a direct scientific legacy of the dinosaur extinction. On biodiversity conservation, lessons from past extinctions stress the urgency of preserving genetic diversity, maintaining habitat connectivity, and fostering ecosystem resilience. Strategies informed by paleoecology aim to buffer species and ecosystems against the compounded stresses of modern environmental change. Public awareness campaigns and educational efforts leverage the compelling narrative of the dinosaurs' extinction to engage societies in sustainability dialogues. The story of ancient catastrophe galvanizes interest in scientific research and environmental stewardship, bridging the gap between deep time and contemporary responsibility. However, challenges remain severe. The interplay of multiple threats, climate change, land use change, pollution, is complex, and rapid action is essential to slow biodiversity loss. Incorporating lessons from Earth's history into policy and resource management is crucial for ensuring a sustainable future. In this light, the extinction of the dinosaurs is not merely a tale of the past, but a cautionary beacon. It illuminates the consequences of unchecked environmental disturbances and the resilience necessary to navigate planetary change. By heeding these scientific warnings, humanity may yet steer Earth's biosphere toward a thriving and diverse future, learning from the echoes of catastrophe that shaped the ancient world. The age of dinosaurs has captured the human imagination for centuries, becoming a potent symbol not only of Earth's distant past, but also of mystery, grandeur, and the fragility of life. Dinosaurs occupy a unique place in popular culture, art, literature, film, and education, shaping how we perceive evolution and extinction. Reconstructing this lost world in our collective memory weaves together science, storytelling, and imagination, offering both an homage to these magnificent creatures and lessons for humanity's place on Earth. From the early fossil discoveries in the 19th century to the latest paleontological breakthroughs, dinosaurs have fascinated scientists and the public alike. The popular image of dinosaurs has evolved dramatically, from lumbering, cold-blooded beasts to dynamic, often feathered animals that exhibited complex behaviors. Media portrayals, from the earliest museum dioramas to blockbuster films like Jurassic Park, have dramatized their life and extinction, embedding dinosaurs deeply into the cultural fabric. Educational materials bring the lost world to classrooms worldwide, inspiring curiosity about Earth's history, biology, and the scientific method. Children's books, documentaries, and museum exhibits translate data from fossils and geology into accessible narratives, fostering a connection across time. Artistic reconstructions rely on a synergy between scientific evidence and imagination. Paleoartists combine anatomy, behavior, and environment to bring dinosaurs back to vivid life, often speculating about colors, sounds, and social interactions. These reconstructions are constantly refined as new fossil discoveries emerge, reflecting science's dynamic nature. Despite our advances, significant mysteries remain, and the process of reconstructing the lost world is ongoing. Ambiguities in fossil interpretation, gaps in the record, and the challenges of inferring behavior from bones make the dinosaurs a perpetual subject of research and debate. Popular culture both shapes and reflects this process, blending fact with fiction in ways that engage but sometimes mislead. Dinosaurs also symbolize extinction and resilience. Their sudden disappearance reminds us of environmental fragility, while the rise of their avian descendants links past to present. This duality enriches their role as cultural icons, signaling both wonder and caution. Moreover, dinosaurs feature prominently in scientific discourse about Earth's history, climate change, and life's evolution, bridging academic study with popular interest. Their story encourages public engagement with science and environmental stewardship. In essence, dinosaurs in popular memory serve as a bridge between ancient Earth and modern humanity. Reconstructing their lost world is an evolving narrative, one where science illuminates the past, culture animates it, and together they inspire a deeper appreciation for the ever-changing story of life on our planet.